All right, so section 9.2 is looking at the central limit theorem and how this applies to sample means. So we want to be able to apply the central limit theorem for sample means to calculate probabilities and also describe the features of the t-distribution. So if certain conditions are met, then what the central theorem does is it assures us that the distribution of sample means follows an approximately normal distribution, right? No matter what the shape of the population distribution is, right? So the population distribution could or could not be normal, right? So here are some conditions that we have to check, right? So if we want to know if we can apply the central limit theorem in order to analyze data, we have to consider these three conditions. Number one, we need a random sample and we need independence, right? Number two, we need a large sample. So we need to know that the population distribution is normal, or I could also have a sample size that is large. So our text recommends having an n bigger than 25. I've seen in a lot of texts where they use 30, right? So 25 we'll use because that's what our text uses, but again, some other statisticians might say no, you need at least 30. Right, so there is some variability there. And then the big third thing is we need a big population. So, and this is similar to the last chapter, right? We need the sample collected without replacement to be at least 10 times larger than the sample size, right? So if all of these are met, then the sampling distribution of x bar is approximately going to be a normal distribution with a mean mu and a standard deviation, right, of sigma divided by the square root of n, right? Or in this case, remember, we use the term standard error here, right, because this is of a sampling distribution. So the larger that the sample size is, the better the approximation becomes, right, it turns out. If the population is normal to begin with, then the sampling distribution is exactly a normal distribution regardless of the sample size, right? So those are some key points to think about. So here's a figure of the distribution of in-state tuition and fees for all tier colleges in the United States for 2012-2013 academic year, right? So notice here that this is a skewed distribution, and we also have multiple modes. Right, so skewed and multimodal. Then on slide 6 here, we're told visualizing distributions of the sample mean. So the figures below show the distribution of the sample mean for sample sizes of 30 and size 90. These are both drawn from the skewed multimodal distribution on the previous slide, right? So what we want to note is that the shape of each is approximately normal, right? And the standard error decreases as the sample size increases, right? So as we get a larger sample size, the standard error decreases, right? And it begins to look more normal, if you will, right? So larger the sample size, the closer we're going to get to that normal distribution. So here's an example. We're looking at weights of a 10-year-old boy, right? So according to data from the National Health and Nutrition Exam Survey, the mean weight of a 10-year-old boy is 88.3 pounds with their standard deviation of 2.06 pounds, right? So we want to assume that the distribution of weights is normal, right? So this is an assumption that we were given. So part A says, suppose we take a random sample of 30 boys from this population. Can we find the approximate probability that the average weight of this sample will be above 89 pounds? If so, find it. If not, explain why. And then here's a second part also that we'll get to, right? So part A, we just read. So you have to consider, so we have a random sample, right? That was given. And we can assume that the population is going to be at least 10 times larger than the sample, right? So the sample size was 10 boys, right? So we can definitely assume that we have at least 100 boys, right? that are 10 years old, right? So we're on this slide, right? So we can assume that. Also, we were told that the population is normal, so since that's the case, we can apply the central limit theorem, right? Notice that my sample size is very small, right? We have 30 boys in part A, so we can still apply the central limit theorem, right? So the distribution of the sample is going to be this, right? I'm going to have a normal distribution. Here's my mean. Here's my standard deviation, right? Or in this case, standard error. So we can use technology to find the probability that the sample mean is greater than 89 pounds, right? So here's a printout of StatCrunch, right? Of doing this, right? So if we plug in the standard error, right, we calculate this, take sigma divided by the square root of n. So we were told sigma was 2.06, and we had a sample of 30. So if we plug that in, we can plug that in as the standard deviation, and then we can type in our conditions here, the mean, and we'll get that the probability that the mean of the sample is greater than 89 pounds is 0.03, right? So this right area, right, is 0.03, which is the probability that something will be bigger than 89, right? The weight is greater than 89 pounds. So we can also find this with the TI graphing calculator in R, just as we have done previously. Right, so let me remind you how to do that. Okay, right, so if we pull up the graphing calculator, I can go to second and then distribution, and we want normal CDF, continuous distribution function, right? And then the lower bound, we would type in 89, right? That's the lower bound. This is the lower bound. The upper bound, it would be positive infinity, right? So we can code that by 1E99. The mean we were given is 88.3. And then this over here, the standard error, we would put in as the standard deviation, right? So if we go to this and hit paste, right, then, so remember, if you don't have the updated version in your calculator, you just have to type this in order, right? So this is exactly how you type it in. You would go to the normal CDF function, and it would give you this with the open parenthesis. Then you would type in 89, the x value, and then you would hit comma, and then type in the, you type in the lower limit, 89, and then you hit comma, type in the upper limit, and then you'll hit comma, type in the mean, then hit comma, and put in the standard deviation, right? And if I hit enter, I get that area, right? 0.03, right? So that's my p-value also, right? If if I'm doing a hypothesis test, right? That's how I get my p-value. Now doing an R is very similar, right? Just a little different. So one thing we have to remember, though, let me grab my pen. One thing we have to remember is R is going to find this area, right? So this is what R wants to use, right? The left area. So if I can use the pnorm command in R to find the p-value of a normal distribution, right? But it's going to find this green. So to find the red, I'm going to have to do 1 minus pnorm, right? Because the green and the red add up to 1. So if R is going to calculate this, then if I do 1 minus that, I'll get what's in the red, right? So type this in, right? So we can do pnorm. So if I do pnorm, and then I'll type in the x value, right, 89, comma, and then I type in the mean, which is 88.3, and then I hit comma and type in standard deviation, 0.3761. Right? Close my parenthesis, hit enter. So this is giving me this green area. So if I hit the right arrow up, I will get what I just typed in, right? And if I put 1 minus in front of that, hit enter, then I'm getting this 0.03 value, right? Which is the red, which is what I want, right? So remember, R always gives you the area to the left, right? All right, so that's just a refresher of what we did previously, right? Finding p-value, same thing. So then this next slide, so we're looking at B now, right? So now let's suppose we take a random sample of 10 boys, right? Can we find the approximate probability the average weight of the sample will be above 89 pounds? If so, find it. If not, explain why, right? So again, we have a random sample. We know the population will be at least 10 times larger than the sample, and the population we were told is normal, right? So we're checking those conditions. So since those conditions are all true, we can apply the central limit theorem, right? And that's even though the sample size is less than 25, right? And that's because we're told that the population is normal. So the distribution of the sample mean is this, right? 88.3, comma, and then my standard deviation or my standard error changed, right? My n value changed. So this is the StatCrunch printout, right? So we had to calculate the standard error and got this 0.6514, right? So that's a larger standard error than we had previously, right? So before we had a standard error of 0.37, right? Now we're at 0.65, right? So nearly double, right? A lot bigger. So then plug that in. We plug in the mean, plug in my value. I'm checking the probability that x is bigger than or equal to 89, and this is what I get, 0.14, right? So the probability that the sample mean is greater than 89 pounds is 0.1413, right? So one thing to note here is that this probability is different than in part A because we have a larger standard error in this case with only a sample of 10, right? So those are some things we have to consider. So then I have another example to look at, looking at home prices. So home prices in a certain community have a distribution that is skewed right. The mean of the home price is 498,000 with a standard deviation of 25,200, right? So we're told that our population is skewed right, right? So suppose we take a random sample of 30 homes in the community. What is the probability that the mean of the sample is between 500,000 and 510,000, right? So part A, we're checking our conditions. So we do have a random sample. We were told that our population is not normal, but we do have a sample size greater than 25, right? 30 homes. So we're okay. And then we can safely assume that there's at least 300 homes in the community, right? 10 times our sample size. So we can apply the central limit theorem, right? So we assume that we're going to have a normal distribution with a sample of or a mean of 498,000 and a standard deviation, or since we're doing a sampling distribution, standard error of this value, right? 25,200 divided by the square root of 30. So going on this slide, I have another printout of StatCrunch. So again, we need to plug in our standard error, need to plug in our mean, and between what values do we want x to be, and here's what we get, right? So if we're doing this in my graphing calculator, right, here's my lower limit, my upper limit, there's my mean, there's my standard deviation. If I plug all those in, I'll get a matching p-value, right? And this is what we're trying to find visually, is this red area, right, in between the lower and upper limit. What's that area? So that area is the probability, so it's 0.3273, right? And then part B is, so suppose we take a random sample of 10 homes now. So could we approximate the probability that the mean of the sample is more than 510,000, right? So because we were told the population of home prices is skewed, then we would need at least a sample size of 25, right, to apply central limit theorem. So since we have a very small sample, we cannot find this probability, right? We need to go back, make our sample size bigger, and then we could do so, right? Right, so I have another example here. This is a good one. So on the next slide, I have three distributions. So one is going to be a distribution of a population. The other two are going to be approximate sample distributions of the sample means, randomly sampled from the population. One has a sample size of 10, one has a sample size of 25, and we want to match the graph with the correct description, right? So here are my three graphs, right? So you want to notice that, you know, this looks about normal, this looks about normal, and this definitely doesn't look normal, right? So the one that definitely doesn't look normal, this is going to be a graph of the population, right? If we had to pick, this would definitely be the best choice for the graph of a population, right? Because remember, the central limit theorem tells us that the sampling distribution for sample means are approximately normal, right? It doesn't tell us that the population is approximately normal, right? So the sampling distribution applies to the sampling distribution. So we take a sample of the population, no matter what the population looks like, right? We get approximately normal. So the next two we have that look approximately normal. Now we have to think about which one would be for a sample size of 25 and which one would be a sample size of 10, right? So one thing we want to remember is as we have a more sample size, right, the standard error, or my spread of the distribution, is going to decrease. So figure A would have a higher standard error than figure C. So figure A would go with right, so figure A would go with the sample size of 10, right? So I noticed here in the PowerPoint I have these backwards. So we want to switch these, right? This should be figure C, and this should be figure A, right? So fix that in your notes. So figure A has more spread, then figure C is the distribution for, or wait, no, I had that right. Excuse me. No, this is right. Figure C would go with sample size of 25, right? There's less spread, right, in this. Figure A has more spread, so we would expect a lower sample than this picture, right? So figure C. So let me just write this here, right? So this has more spread than this guy, right? So I would let me get rid of this. All right. So the standard error over here. So if I let I don't know, x be the standard error over here, and y equal the standard error over here, x is going to be bigger than y, right? This has a higher standard error. Figure A has a higher standard error, more spread. So if we know that as sample size increases, the standard error decreases, right? So since this has a higher standard error, we would expect this to be the lower sample size. So this would be a sample size of 10, and this should be a sample size of 25, right? And actually, for this sentence to make sense, I probably wouldn't have switched. Let me fix this. So let me get off of my pen. I probably wouldn't have switched the C and A. It probably makes more sense to switch the numbers, right? So make this sample size 10 and this sample size 25, right? That probably makes more sense in the flow of the sentence, right? So since figure A has more spread than figure C, then figure A is the distribution for sample size 10, and figure C is a distribution for a sample size of 25, right? All right, so we got that fixed. So sorry about that typo there. All right. So then one thing that we're going to use is the t-statistic. So it turns out that when we're dealing with sampling distributions of a mean, a different type of distribution than the z, called the t-distribution, is a better fit, right? So there's actually a little bit about this in the text, a little bit about the history of how the t-distribution was found, right? So you can read over that if you'd like in the section. So hypothesis tests and confidence intervals for estimating and testing the mean are based on this t-statistic. And typically we don't know sigma, right? We don't know the population standard deviation. Then we estimate this by using s divided by square root of n, right? So this is our approximation for sigma, right? So we can use this as our calculation. So you definitely need to know this equation, right? T equals x bar minus mean divided by s divided by square root of n, right? So s divided by square root of n is going to be our standard error estimate, right? So I can just write this in, right? This part is my standard error estimate, right? Remember, this is going to be my sample mean, and this is my population mean, right? And this t is just so instead of using the z statistic, we're going to use the t statistic, right? So it's just a different distribution. So in the next two slides, we'll learn more about the t distribution. So the t statistic does not follow a normal distribution, right? And that's because my denominator changes with every sample size, right? Because if we look at the t statistic, this denominator will change with every sample size. So a different sample size means a different denominator. So the t statistic is more variable than the z statistic, right? We have more variation, right? With the z statistic, my denominator is always the same. So if my three conditions hold for the central limit theorem, it follows that the t statistic follows a distribution called the t distribution, right? So on the next slide, we get to see what the t distribution is. So the t distribution is still symmetric and still bell-shaped, right? But the difference is we tend to have thicker tails in the normal distribution, right? So you can see that. So this line here, right? This line is the t. So notice there's more area. They're thicker tails, right? That's what we're meaning. There's more area with this than the normal distribution, right? So you can maybe see that better now that I erased, right? So there's more area, right? They're thicker tails, right? Also, my shape is going to depend on what we call degrees of freedom, right? And we're going to learn more about that, right? So depending on what the degrees of freedom, my T shape changes, right? And we'll learn some more about that in the future. So if my degree of freedom is small, then my tails are thick, right? As my degrees of freedom increases, my tails get thinner. So as my degrees of freedom get larger, then we become more normal distribution. My tails get thinner, right? All right, so here's a picture that I found on the web to help kind of put this home, right? So another thing to note is that degree of freedom is equal to n minus 1, right? Where n is my sample size. So as my sample size gets larger, my degrees of freedom gets larger, right? So the top line, this black line, that's my z curve, right? My normal distribution. And then we have n equals 3, 5, 20, and 30. So we can see what happens as we increase the sample size, which increases the degrees of freedom, right? So as we increase the sample size, notice this red line is a lower degree of freedom, where the blue line is higher, right? So as my sample size gets larger and larger, we get closer and closer to a normal distribution, right? So that's why we use a t distribution here, because it's a better fit for the means, right? So before we use z statistic, now we're going to use the t statistic. So the probabilities are also different, right? So we have to use a different table or a different way to find those on our graphing calculator in R, right? And I will show you how to do that in the future, right? So there is the central limit theorem for a sampling distribution of the population mean, right? So central limit theorem for sample means.